It took me to dust.
To go.
Hello and welcome back. I hope that we have the audience with us. So as a reminder, please do post your questions in the Q&A section, and we will pull that up at the end of the talk. And also keep the chat live, and I will post the link to the Slack channel. So after the talks, we can keep the conversation going there. So it's my pleasure to introduce our second speaker in this session, Matthew Feichert, and he will talk about distributed statistical inference. Take it away.
All right, thanks very much. And then let's see, Ben, if you can hide yourself as well, that'd be great. Okay, so for those who are interested in having the slides as well, I'm just dropping that link in the talk, and so you can check those out if you want. I'm now going to share. Okay, should be sharing now. Okay. Right, so thanks very much for coming to this talk. And so this is we're going to be kind of covering example use cases of distributed statistical inference with pyhf powered by funcX. And I'm going to be presenting today on behalf of myself, as well as the rest of the pyhf core development team, which comprises of Lucas Heinrich, who is a CERN fellow. Myself, I'm a postdoc at the University of Illinois at Urbana-Champaign. Jordan Stark, who is a postdoc at the University of Santa Cruz, and then as well as Ben Galuski, who is our colleague and is at NCSA as well as Illinois, and is also a developer of funcX. Okay, so just to kind of get going, so myself, Lucas, and Jordan, we are all experimental high-energy particle physicists, and so we are part of an experimental collaboration known as ATLAS, which is one of the 4 big experimental collaborations that are located at the Large Hadron Collider at CERN, which is just outside of beautiful Geneva, Switzerland, and in Switzer, France, basically. And so on the left-hand side, you can see here this kind of obligatory picture of the Large Hadron Collider's huge 27-kilometer circumference ring that's kind of superimposed on the countryside, and as well as annotations of where the main detectors would reside, but they're about 100 meters below ground. And so, as I mentioned, we're part of ATLAS, but the ATLAS collaboration is formed around the ATLAS experiment, which is this, you can kind of think of it as a cathedral-sized digital camera for looking at particle collisions, seen here on the right-hand side with a T-Rex to scale. And the reason that we're doing these experiments and we're colliding these protons at some of the highest energy densities possible is because we want to try and better understand the fundamental interactions of matter with the fundamental forces of the universe. So we're interested in how things like electricity and magnetism, as well as the strong and weak nuclear forces interact. And thanks to a long history of success and lots of hard work, we've been able to basically describe all of these interactions so far in a single mathematical framework known as the Standard Model. With a little bit of tweaking, you can kind of fit on the side of a coffee cup shown here. But we know that that's not, a perfect description of all of nature at the fundamental levels. And so at this point, we're still trying to learn more about the physics we do know about, such as things like the Higgs boson that we found in 2012. And we're also trying to search for new types of physics like dark matter, or understand dark matter better. Okay, but I've been discussing what things are like at the LHC, and we can kind of go through what are the general goals of doing physics analysis at the LHC. So as I mentioned, we're hunters and searchers for new physics. So we're, as I mentioned, the Higgs boson that we found in 2012, which shows up as this little bump here on this plot. And when we do find new physics, we want to try and really understand it and characterize it. So we want to try and make precision measurements of those particles and those processes. So we try and work together in our experimental collaborations and also in global collaborations to try and make precision measurements of these properties. But then also there's many times where most times actually where we don't find new physics, but we still want to make sure that our work is useful. So we try and constrain the different theory parameters of the models by setting the best limits possible on these different processes. So all of this work, it requires building statistical models and then fitting those models to data to try and perform statistical inference. But especially for some of these like much more large scale searches, the model complexity can be huge and it can balloon pretty fast. So this is traditionally a problem because this now means that to actually fit your statistical models, this can take many, many hours, sometimes in the most extreme cases, days, and that's not great. So as a goal of pyhf, what we want to try and do is we want to empower physics analysts with fast fits as well as expressive models. Okay, so on slide 4, I'm just going to give a real quick one-slide introduction to what pyhf is, and then we can move on. But pyhf is a pure Python implementation of a ubiquitously used statistical model in high-energy physics known as HistFactory, which is basically a specification for a family of statistical models for multi-bin histogram-based analysis. And out of the box, we support multiple computational backends and optimizers. And so if you just do pip install pyhf, you'll get a NumPy backend as well as a SciPy optimizer, which already works great. But we also support different computational backends. We support JAX, we support TensorFlow and PyTorch, as well as their optimizers. And what's nice about these ones is that we can leverage their hardware acceleration features on both GPUs as well as TPUs, as well as also really take advantage of their automatic differentiation features, which helps a lot in the minimization. And so through the combination of these different features, along with the highly vectorized approach of all these different libraries, we're actually able to outperform some of the traditional C++ implementations of these models that are kind of the default in high-energy physics right now. So if you want to learn more about pyhf, I'd encourage you to do so. In this tutorial, or in this link to the slides, all of these down here at the bottom are hyperlinked. So you can either check out our tutorial, which is Jupyter book based. So thanks very much to the Executable Books team. You can also read our paper in the Journal of Open Source Software. And if you want to, you can also check out our talk from SciPy 2020 last year about pyhf in general. Okay, but so I talked about how pyhf is useful for accelerating statistical inference, but we'd also like to try and scale this out as much as possible. And so a kind of natural way to do this is to think about using functions as a service to try and do this at scale. And maybe a natural habitat for functions as a service is cloud providers, because they give a nice platform that's robust that can scale elastically. And as an example of this GIF that you're seeing on the right-hand side is an example of pyhf running across 25 worker nodes on Google Cloud Platform, where it is running a real LHC physics analysis while doing the final stages of the statistical inference, that is, where the results are being, the different mass hypotheses are being evaluated on GCP, and then the results are being plotted and streamed back in real time. And so through this distributed method, we're able to do this entire analysis and this final stage of this analysis in just under 3 minutes. So that's obviously a very nice and powerful resource, but cloud computing is something that, at least in my sector of academic sciences, is still something that is growing and we're still trying to get better experience with. And I kind of like to think of cloud computing also as having a paying for priority model. You are getting super fast, responsive compute, and that also has really reliable uptime. But it also, you have to pay for it, which makes sense, of course. And even with some of the really nice support from cloud providers and giving scientists cloud credits, it still requires funding at some stage. So on slide 6, what I'm going to suggest is that as maybe one alternative to consider is looking at HPC, high-performance computing facilities, which are much more commonly available for use in high-energy physics and provide an opportunity for efficient performance of statistical inference, given their large compute capabilities. However, I think everyone who's had some experience working on HPC systems before can attest that there's a bit of startup cost, especially if you're a new student trying to just get used to the orchestration and the different batch scheduling systems. And so this can be a little bit difficult if you just want to do some physics right away. But it would be really nice, especially when we have a lot of HPC systems that actually have GPUs on them, to be able to try and leverage the pyhf hardware acceleration, which has a big kick to it. So on this right-hand side, we can see just kind of one particular example of kind of a large computational, a large statistical model that in some of the traditional C++ frameworks took over an hour to properly fit, that when we transparently put it on GPUs with our JAX backend is able to get a similar result in under a minute, which we don't obviously want to try and leverage that. So what we're considering is trying to deploy pyhf on HPC systems, but using a fitting function as a service. And we'd like to try and leverage this for large-scale statistical ensemble fits, as well as very large theory space parameter scans. Okay, so on slide 7, the way that we're proposing doing this is by using funcX, which is designed to, it's a high-performance function as a service platform, and it's designed to orchestrate different scientific workloads across heterogeneous compute. So that's anything from clusters all the way through supercomputers. And it also supports a wide array of task execution. So HTC Condor, Slurm, Torque, all your favorites, as well as Kubernetes, which is also really nice. And it does this by leveraging Parcel, which is a very nice parallel scripting library in Python for very efficient parallelism and also managing concurrent task execution. And kind of the high-level overview of this is it allows you to register and execute Python functions in a serverless supercomputing workflow. And it also provides a very nice Python API through their software developer kit that allows you to interface with the funcX services that are running. And all this is kind of done through a controlling funcX endpoint, and that's running on your execution machine, and then your submissions machine can actually be totally separate because all the communications between the two happen through Globus. And so this is pretty sweet because it allows for kind of a fire and forget remote execution model where you can just write some pure Python on your laptop, send off your jobs, close it, and then if you want to, later on, retrieve that output. And so this is a tool that's in the growing ecosystem of distributed computing. Myself and some of my other colleagues on Atlas are also starting to look at using Dask as well. But so this is just one of the pieces that is out there that we're looking at. Right, so I'm going to try and do a little bit of some live demoing stuff, and we'll see how this goes. But right now, I'm just going to try and show you kind of a toy example of what it would actually look like to turn a compute resource into a funcX endpoint. So I'm going to switch over here, and hopefully I can get some thumbs up if there are, if people can see the terminal okay. I'm going to assume so. And I can't actually see anything at the moment. So what I'm going to do right now is I'm first just going to clone down this particular example, which is the stock repository. Okay, and we're just going to CD into that. Right, so if we look inside here, you'll see that I actually already have a Python virtual environment that is set up, and that's just for the benefit of time, just because I don't want to pip install everything. But if we look inside of this core requirements file, we see that there's really not much there. There's just funcX and funcX endpoint, and then also because we want to set up the tools we need to do our fits on our endpoint, then we also have pyhf as well as some of its contrib modules. So if I was, so here I'm going to do all this as kind of a toy example just on my local machine, which could actually work if I wanted to turn my laptop into a funcX endpoint. But here I'm just, but this, you can imagine this was actually being done on the University of Chicago's River cluster. So there I would just Python pip install our core requirements, and that would be great. And now once I've done that, then I have access to the funcX endpoint command line interface. So what we're going to do, actually, let me just double check. Is that gone? Yeah, okay, that's gone. So what we're going to do is we're going to use the funcX endpoint command line CLI to configure and set up a funcX endpoint for execution. So I'm going to make one called pyhf. And since this is the first time that I'm doing anything on this machine, I'm going to first be asked to use Globus to do some authentication. And so here I'm already logged in, but if you aren't, you would need to make a Globus account, but that's pretty easy given everything that they support. Okay, so I now get a limited time, I now get a limited time, I now get a limited time authorization code, which I can go ahead and paste in. And now Globus has authenticated me here, and it tells me, hey, you're good to go. You can set up a profile and get computing. So if we were actually at the University of Chicago's River Cluster, then we would probably want to look at the config that we have there, where we can see we're actually going to be, we would be utilizing the Kubernetes provider as well as the high throughput executor. But in this situation, and so there we would just go ahead and copy that config file into our funcX directory and overwrite the default config. But today I'm just going to kind of show what it would be like if you got up and running with just locally. So we would do funcX endpoint start, and then the name of our configured endpoint. And boom, we now see that we have a daemon up and running. And if we also do funcX endpoint list, we can see that we actually have an endpoint running here. So we could actually start sending jobs to my machine, but at the moment we actually have something set up running at the University of Chicago. Okay, so switching back to the presentation for a second, I'm just going to focus on what the endpoint is for a little bit. So it's a logical entity that represents the compute resource, and it also, along with it, has an agent process that allows for managing it in terms of resource execution. And this agent, through Globus, handles all the authentication and authorization, which is really nice, as well as also requesting compute nodes. And we can see if also on the right-hand side, this is that same config that I just showed you, and this is one that's currently running at River right now. And so this is where you get to kind of use your expert level knowledge about the compute resource that you're using to try and configure it to best utilize the resource you have for the problem that you want to try and work on. So you can see here that Ben has set this up. Thank you, Ben, to make sure that it has plenty of memory, and then it's also using the Kubernetes provider to be able to use a particular Docker image that he's set up that already has all of our requirements set up in it as well. Okay, so moving on to slide 10, we're now going to turn. So that's all been focusing on the execution machine and setting up an endpoint. We're now going to turn to the user side of defining user functions. So this is, we're talking about running functions as a service. And so the first thing we need to do is define these functions we want to run. And so as an analyst, you can do this very easily using the software development kit that funcX provides just in a Python script. So here we're defining user functions. We're defining a preparation one for our workflow, and then we're also defining an inference hypothesis test function. And you'll note also that as these functions are going to be run as individual independent jobs, they're going to require that all of their dependencies are actually defined inside the function. So that's why you have these import pyhf statements inside of the functions, and because we want to make sure that they're actually in scope. And then on slide 11, now that we've defined our functions, we need to register them with the funcX client. So the first thing we do is we, in our Python script, we go ahead and initialize a client, and we also make it aware of the endpoint that it needs to be talking to. And now we just take our, here we're just going to do this for first our preparation stage. So we're going to prepare this, we're going to take our prepare function and we're going to register it with funcX client so that it knows about it. And then we're going to use this run command to then have funcX serialize our function send it out to the endpoint, wherever that is in the world, and actually run that. And then while that's happening, we're then going to periodically wait on it and then make periodic requests to get the results back of that compute job. And so we can now try and scale this out. So this workflow of registering functions and then running those functions, this is something that we can now kind of try and do more at scale with our inference system. So here we're going to register our inference function with funcX. And now we're, so in this pyhf patch set, this basically contains all of the signal model hypotheses that we want to test for our physics analysis. And so we're simply going to just loop through them and then just fire them off. And this is actually not maybe the best way to do things, but for this example, it works. And then while those are all running, we're just going to, they're going to be running simultaneously, and we're submitting these just from our laptop. We're not actually doing anything special, and this has all just been written in pure Python, so it's pretty nice and pretty fast to get going. So as an example of this, we're going to try and actually run this live here. So we're going to try and submit a analysis, if I can spell, using a particular configuration file for an Atlas analysis that is published, and let's run with the JAX backend. And so this is now submitting, and if I flip back for a second while that's warming up, so what it's currently doing is it's getting this these data products that define the analysis that we published through Atlas off of the HEP data repository, and it's pulling those down to the submit machine. It's now registering all of our functions on my submit machine, my laptop, and then serializing them and sending them off to the funcX endpoint. Execute, and now it's going to be executing all those jobs as well. And then as it comes back, it should retrieve those and come back. And so all of that can run, and we're doing an entire physics analysis that traditionally would take at least multiple hours, if not days, in the minute time frame. And so if we flip back to here, so those are still running, but so I'll maybe go ahead and move on. But so this is going to be running all in under a few minutes, and we currently have deployments of funcX spread across different clusters, both University of Chicago, NCSA Blue Waters at Illinois, as well as Exceed. Yeah, and so we can see that we're already getting results coming back right now, and as it's periodic, it's also we'll just checking to see if there's pending tasks, but things are coming in pretty nicely, so we might just go ahead and wait. Yes, boom. Okay, a minute 32 seconds to do an entire physics analysis. That's not too bad. And now, so if we look at actually what was returned to us, so we have a results.json file. And if we go ahead and peek inside with that with JQ, so if we do JQ, let's get this one right here, result, and then results.json. Then we see that we have this return structure that is just in the form of JSON, where we have the metadata about the actual signal mass hypothesis that was tested, the modified p-value that we actually care about, as well as some information about the fit time. And if we flip back, also there's an ASCII cinema if you want to watch that later. If we flip back and actually look at what this is again, this is simply just the return structure of our inference function. And so you can see here that we've defined the metadata, CLS observed, and fit time, and that's exactly what we get back over here. So this is kind of cool because this the way that we've defined this, we've been able to just write a very simple inference function in a Python script, and we've been able to serialize this, do compute, get things back, and in a nice format that we're able to both play around with at the command line, as well as also ingest and start to do some visualization. So this means that you can go from submitting jobs to having plots in just a few minutes. Okay, so now in closing, just to try and talk about some constraints and trade-offs that we're seeing at the moment. So for the nature of functions as a service, for it to be so highly scalable, this also means that it can't really take advantage, at least as far as I'm aware of using just-in-time compilation. So just-in-time compilation can be super helpful and speed up work quite a bit. So the right-hand side shows an example taken from the JAX documentation, where from just doing a very simple JIT compilation on an expensive computation, they're able to get a 50 times speed up, which is great. And we'd like to try and leverage this for performing pseudo-experiment generation. But a problem is that there needs to be preserved memory that is preserved and shared across all invocations for us to do this. And by the nature of functions as a service, each of the functions will be self-contained and don't know about a global state. So that's one thing that we're running into that we can try and deal with by just scaling out, but this is something we don't have advantage to. And of course, there's no magic bullet. You still need to, even though you're not writing bespoke submission files to Slurm or something like that, you still need to be able to tune funcX to your specific resource, and that requires expert knowledge of your HPC system. Okay, so in summary, through a combined use of pure Python libraries, funcX and pyhf, we demonstrated the ability to both parallelize and accelerate statistical inference for real published physics analysis from the LHC. And we did this all without having to write any bespoke batch jobs. And this can basically be done by an analyst using a nice Python API that still achieve really large performance gains. And we were able to do this while transparently switching between provider systems, as well as also, I didn't show this, but you can switch between CPU and GPU environments in a similar way. But we can't yet leverage JIT operations. And all of this code that I've shown here is public and open source on GitHub, as are pyhf and funcX. And so thanks very much for listening. And I would invite you to come talk with us. And I'll just mention in closing that pyhf is a scikit-het project that is funded in part by IRIS-HEP, which is the Institute for Research and Innovation in Software for High Energy Physics, which is itself an NSF-funded project. So if you have any questions, I'm more than happy to try and address them now.
Thank you very much for the talk. So we have a couple of questions in the Q&A. So I'm pulling those up. So the first one from Andrew is this: how does this interact with cluster networks? Do the compute nodes need to be able to see globals?
So Ben might be able to give more of an informed answer than I can, but okay, he's also got his camera on now, so I'll go ahead and let him talk.
All right. Yeah, so this has been designed to run on a wide variety of HPC systems, and so there's endpoint code which has to run on like a head node or a login node that has connections out to the world, and then all the internal communication happens inside the HPC. So we work on a number of HPC installations where the worker nodes have no access to the internet, and so there's this architecture is designed to route the tasks down to the workers, get the results, and send them back. Is that? I think that was the question.
Thank you. So I'm pulling up the second question. Does pyhf has Docker support?
Yes, it does. So we have a default Docker image that is just under pyhf, but obviously there are some situations in which you want to be able to just have a containerized solution that has NVIDIA support. So we've also very recently started supporting these NVIDIA CUDA images, which I will warn you are huge because of the nature of the fact that Python is obviously not compiled. But they do run on HPC systems and also like anything that has NVIDIA support. So they're available right now off of both Docker Hub as well as GitHub Container Registry. So feel free to just to Docker pull those down and open up any issues in case you have questions or use issues.
Thank you. And then the last question. Okay, sorry. So does register function grab the code later on?
So I'm not quite sure about what code literal might mean, but it does use pickle to pickle the function and then send it on down. And then it also keeps track of the actual ASCII code for in case you can't make the pickle.
Okay, thank you. I think we are running out of time. There are a few more questions in the Q&A, so I would invite people to use the Slack channel to follow up on those. And thank you again for the talk.
Yeah, thanks so much.